Welcome back to our second part on timers and PWM generation. My name is Jose Quiñones, Applications Engineer for the Power Application Controller. On our previous video, we went through some of the topics such as what is pulse width modulation, how does the timer peripheral works, and how we generate dead time. Today I want to show you some real-time timing examples on the lab. For your reference on this tutorial, we will be using a PAC5523 evaluation platform interconnected as shown on this picture. We have a video detailing how to perform this set of connections, so be sure to watch this resource at your convenience. Okay, so what I'm going to try to do here is show you two things: the graphical user interface that I'm going to use to control our three-phase inverter, and then the output on the oscilloscope. So what I have in here is a motor, a Hall sensor motor connected, but I have only connected the Hall sensors because what that's going to allow me is to control the three-phase inverter output without driving a motor. If we drive the motor, then it's going to go and we're not going to be able to see the signals in question. The other aspect that I wanted to mention is that I have disabled the speed PI and the current PI because I want to show you the PWM. And of course, the only way to control the PWM is if we are on PWM mode. If you disable the current PI and the speed PI, we are in PWM mode. So now what I can do is put a number in here to say 100. That's 100 ticks. Everything is in ticks here because we want to basically just send the numbers that the firmware is going to use to drive the motor as they are. We could have done percentage, but then we have to convert it into something that the microcontroller understands, and that will be ticks. So we're just doing it in ticks. Now I'm going to enable my motor, and you're going to see that's the PWM output. The other thing that I wanted to mention is that we have this little window here called Live Debug, and I'm going to be showing you a few things. Basically, it is a series of variables, internal variables that you can see in real time how they change. Like for example, right now I have my PWM duty, and if I were to move this scroll bar, you can see that both the PWM duty is changing. So basically, that's just what I did. I just wrote 239, so this is what the firmware has, 239. But you also saw that the PWM is changing with as I change it with the graphical user interface. But before I go into PWM, let me show you the basics. First thing we talked was the period. And when you change the period, you're changing the frequency. If you look at the scope, you're going to notice that our frequency right now is 100. That's the default on the firmware, is 100 kilohertz. But you can change it here. And when you change the frequency, what you're changing is the period, if you remember from the previous video. So let me show you something here in the live debug. I'm going to change now to PWM period ticks, and the default for 100 kilohertz is 1000 ticks. So 1000 ticks corresponds to 100 kilohertz, and there is an equation that you can look in the firmware to see how we derive that. But if I were to change the frequency here, what I am doing is actually changing that period, because that's what we control. We control until what tick count the timer is going to count. For example, if I go to 99, that would be 1010. And if you look at the oscilloscope, the frequency went down to 99 kilohertz. You can also write here, let's say 75, and now the frequency went to 75 kilohertz, and the number of ticks on the period is 1333. So that means that the counter is counting from 0 to 1333. In my firmware, in the back EMI firmware, the 6-step traversal, we use up mode. But if this was field oriented control, we will be using up down. And in that case, it will be counting from 0 to 1333 and then down to 0 again. Okay, so that's the PWM frequency, which is nothing other than changing the period of the timer. Okay, so now I want to go back to 100 kilohertz. The next demonstration I want to show you is the duty cycle. Remember, once you set up your switching frequency, that's the PWM frequency, and that's how many cycles you're going to get per second. Now, the duty cycle, the actual duty cycle, is the number that we're going to put on the CCR register. In other words, if you recall from the previous video, the moment in which we disable the output. So if you look at the scope, what you're going to see is that the time that it goes high, that's the beginning when we start counting as 0. And then when it goes low, that is the moment when we find the CCR. So when I change this number, let's say I put a 200 in here, that's 20% duty cycle because it's going to count up to 1000. So 200 out of 1000 is 20% duty cycle. That's what the CCR got updated to. So when I change this value here, I am changing an internal variable called duty cycle that is fed into the CCR for this PWM output. Okay, and that is happening, obviously it's happening in real time, and the firmware is updating the CCR register, and then the hardware takes over, and every single PWM cycle is basically generated with that duty cycle. All right, for my last demonstration, I want to show you the dead time generation, but for that I have to change the scope probe so that you can see the fed gate drive. So the channel 1 is going to be the low side, channel 2 is going to be the high side fed gate drive, and then the channel 3 is going to be the output. So as we can see on the scope, when I enable the phase, this is going to be phase U, you're going to see that the low side is going to be getting disabled when the high side is getting enabled, and that makes our output high. Okay, that's when we're driving the motor. That's when we are allowing current to go into the winding. Now, if you recall from the previous video, we really cannot let those two FETs conduct at the same time, and you can already see a little bit of a delay from the moment in which the low side is disabled to the moment in which the high side is enabled. And right now that is at 250 nanoseconds. I can change that amount of time, and you're supposed to change that amount of time to ensure that your FET is being driven correctly, because we want to avoid shoot through. And we do that by changing the dead time, that delay that we have to put on that register for the dead time generator. So if I were to move this slider, you'll notice that my dead time changes. I can make it bigger or smaller. And of course, you don't want to make it too small, because then you're going to get shoot through. But when I change this value, only one of the dead times changes. So you have one control for the rising edge and one for the trailing edge. And you can see how I can change the dead time on a per edge basis. All right, I hope this demonstration on timers, PWM generation, frequency generation, and dead time generation has been useful for you, and that you can understand these topics a little bit better. I do want to thank you for spending some time with us, and I'm going to see you on the next one.